Okay, so we now know that we can make ions mutually benefit each other through a give and take of electrons from one thing to another. Typically, we see a give of electrons from a metal and the take for the nonmetal. So a metal gives an electron or more to a nonmetal. We may need more than one atom of each to make the kind of benefit work out for everyone, to get everything satisfied and happy with the octet rule, but that's okay. As long as we can get everything to an octet or a duet, okay, and everything ends up being more stable that way, we're good to go. The good sign of this is that all the charge cancels. So all of the positive charges from the cations that we make should cancel perfectly with all the negative charge of the anions that we make. It's a good sign that we've got a good give and take that benefits everything. Okay, so we're going to look at some more examples that get a little bit tougher. So we're going to try and make an ionic bond and therefore form an ionic compound using the elements silver and chlorine. Okay? So, as usual, I would just go look at the periodic table and see how many valence electrons something starts with and use that to figure out how many it gains or loses. So I go find silver on the periodic table, and it's in the middle. It's in that valley of the periodic table where we don't have a shortcut for how many valence electrons it has. Now, just based on the electron configuration, usually you'd think it would have 2 valence electrons. But there's some weird stuff that happens on the periodic table in that middle section with these metals. Okay, they're not so predictable. With something like magnesium or calcium or strontium in the second column, those guys have 2 valence electrons, and so we are sure they're going to lose 2 valence electrons to back up to a previous noble gas configuration, to become a stable ion, to get an octet. But the metals in the middle section of the periodic table, we call those the transition metals, are a little bit wonky. Sometimes they'll give up 2 electrons, sometimes they give up 3, sometimes 1, sometimes 5. They're variable. There's a complexity to how they stabilize and how they give up and kind of remove electrons and pass them on to something else. So how do we figure out how many electrons to give away from a metal like this? Well, we use a little Roman numeral like that to signify how many valence electrons a metal, like the transition metals in the middle of the periodic table, how many electrons the element is willing to give up in this case. Again, case by case, sometimes that number changes. But in this case, this Roman numeral 1 means that silver is going to give up 1 electron for every atom of silver that's involved. So it's going to give up 1 valence electron. Okay, since electrons are negatively charged, we can figure that means it should have a positive 1 charge. Okay, so rather than looking for the periodic table to figure these out, if we've got a transition metal like silver or chromium or ruthenium or vanadium, we're going to look at that Roman numeral. That's going to tell us how many electrons we're giving up, and therefore how charged that ion is going to be. Okay? We're also always going to assume that these transition metals give electrons, not take electrons. So it's always going to be how many valence electrons they're giving up and how positive they become, not the other way around, taking and getting negative. So again, this Roman numeral 1 is indicating that silver is going to give up 1 valence electron. Anytime I have an atom of silver in this compound, silver is going to give up 1 valence electron, which means it's going to have a positive 1 charge. Right? Thankfully, this other part is something we can recognize and do just the same. Chlorine is in column 17, so it should start with 7 valence electrons, and it should gain 1 valence electron to become more stable. So it should end up with a charge of -1, which we write as 1 minus. Yeah, backwards. Okay. With that, we can now draw out what the formation of this ionic compound is going to look like. So for my transition metal, I'm only going to show as many electrons as that metal is going to give up. So since silver is looking to give up 1 valence electron, I'm just going to draw 1 valence electron. Okay. Since chlorine starts with 7 valence electrons as normal, I'm still going to do 7 valence electrons just like I normally would. So how do I get these both to benefit from this situation? Well, silver is looking to lose that 1 valence electron, and chlorine is looking to gain that 1 valence electron. So, pass that along. Give silver's electron over to chlorine, and what we're left with is silver that's lost all its valence electrons. That means it should have kind of a full set in the energy level underneath, making it stable. And it should have a +1 charge. Again, on here you can write it as 1 plus, but the 1 is implied, so I'm just going to write plus. My chlorine now has its original 7 valence electrons. But also that extra 1 it took from silver. Oops. Yep. Meaning it now has a negative charge, which I write as just a negative. The 1 is implied. All right. So, because these metals have this kind of ability to give a different number of electrons depending on the situation, depending on what they're bonding with, we need to indicate in the name of the compound how many electrons something is willing to give up. So, for example, if I were to write this normally, the cation name comes first, followed by the anion, with the IDE ending. Okay? You might expect this to look something like silver, chloride, which makes sense, and it is mostly right. Okay? But from an observer standpoint, let's say we were trying to figure out what silver chloride was made of just based on this name. Okay, well, is silver going to give up 1 valence electron, or is it going to give up 2? That can greatly change what my formula is going to end up being. So this isn't going to be satisfactory. I need something else in there. Well, I mean, this Roman numeral wasn't just telling us how many valence electrons something is going to give up. So really, the place you're going to see this most is in the name of that ionic compound. So right after the cation name, we're going to throw in the Roman numeral. This I stands for 1. Now, technically, that Roman numeral goes directly after the cation name, which means there's no space in between. It's not silver space and then our Roman numeral. And we always do it in parentheses. So it's kind of the technicality of it. I don't usually go nitpicking on it, and it honestly bugs me. I feel like this looks wrong. Like, Microsoft Word is going to kind of put a red line underneath it for me or something. Like, you missed a space. But that's just how it's been, and I guess that's probably how it's always going to be. And I'm sure it's because we want to make sure that all this is held together so we know the Roman numerals with that specific metal. Okay, so we've got silver 1, chloride. That is the name of this ionic compound. That way, if someone were to take this name, they could figure out what it was made of. They could figure out this structure here. All right? The formula is just going to be how many atoms of each element we needed to make this thing happy. All we needed was 1 silver atom to make that cation, and a chloride anion, and that's it. The electrons did the rest. So our formula is just going to be AgCl. Note that the Roman numeral is not in the formula. Now you might be saying, well, hold on. We needed to put it in the name so we could figure out how this thing bonded. If we don't have the Roman numeral in with silver here, how can I figure out what this substance would look like? Well, I might not be sure about how many valence electrons silver is going to give up, but I am sure that chlorine is going to start with 7 valence electrons and needs to gain 1. So that tells me something. In order to make AgCl happy, it needs 1 valence electron to be given to the chlorine, which means silver's got to be giving up 1 valence electron. Okay? So I can figure it out based on usually the nonmetal that is more strict on how many electrons it needs. Okay? If chlorine needs 1 negative electron to kind of become satisfied, then silver's got to give that 1 up. If we were dealing with something like oxygen or sulfur that needed 2 electrons, then our metal would need to give up 2 electrons. Okay? And be aware that this goes for things that have multiple atoms of the metal or the nonmetal. So if I had a substance like we're going to see in this next one, it might take a couple atoms of each element, and that's okay. We can still figure out the charge kind of and go backwards on it to figure out how many valence electrons that metal lost. Okay? So for now, to wrap up this one, before we get in too deep on this, this is the structure of our ionic compound that we can call as a name silver 1 chloride. Or as a formula, we can call it AgCl. Because of this give and take of electrons, we end up with this attraction between the positive ion, the cation, and the negative ion, the anion. And that attraction between those ions is called an ionic bond. And together, those elements, now ions, okay, make a new substance with new properties we call an ionic compound. So this is now an ionic compound held together by that attraction ionic bond. So let's try a tougher example. Make ionic bonds between copper 2 and chlorine. And in case you don't know your Roman numerals, which, you don't usually need them nowadays, so I'd understand. Write them out over here. I is 1. I is 2. I is 3. IV is 4. V is 5. VI is 6. VII is 7. VIII is 8. IX is 9. and X is 10. You don't really have to memorize these. If you ever really need to know a Roman numeral, you can ask me, okay? Or you can look it up and get a list, okay? But a trick to help you out, there are 3 fundamental letters here. There's an I, there's a V, and there's an X. Right? The I again equals 1. V equals 5. And X equals 10. All right? Having the same number next to each other, like in this II or this III, means those numbers are adding. Right? And if we have 2 different numbers next to each other, like this VI, okay, or like this IV, it's either going to be adding or subtracting. If you have a number before that kind of bigger letter, like the V is 5, I is 1, that means we're subtracting 1 out of 5. So this winds up being 4. You can kind of think of it as 1 out of 5. So if we take 1 out of 5, we're left with 4. On the other hand, if our smaller number comes after that letter, it ends up adding. So VI is saying 5 and another 1. So that would be 6. Okay, so VII would be 7 because it's 5 and 1 and 1, so 7. Okay, and so on and so on. IX would be 1 out of 10. So you take 1 out of 10, you're left with 9. So again, you don't really need to memorize them, but hopefully if you kind of remember that I is 1, V is 5, and X is 10, that should save you a lot of work, save you some brain space. Also, as far as the way we use this in chemistry, we don't often go past 6 or 7. Usually that's about as far as we go. Since we're looking at losing valence electrons, we don't often hit a case where something gives up, 8 valence electrons all of a sudden. Typically, the problems we're going to see in this class, we don't even really go much farther above 4. So realistically, 1 through 4, I, and IV, are the ones that are good to recognize. Will make your life easier if you can recognize them. Having the V and VI is also kind of helpful, but we don't see those nearly as often as these other ones. These are kind of the popular ones here. Okay, so to get back to our problem, copper with a Roman numeral 2 means that copper is looking to lose 2 valence electrons. Okay, that means it's going to have a charge of positive 2. 2 plus. Right, chlorine, just like before, has 7 valence electrons. It's looking to gain 1 valence electron, which would leave it with a negative 1 charge. Okay, so let's try drawing this out. All right, in this case, our copper is going to have 2 valence electrons drawn because it has 2. It's going to look to give up. So I'm just going to give this guy 2 dots. And I can kind of already tell by the way this is drawn, like I'm going to be kind of giving away here. So that kind of gives me a hint. Okay, each chlorine has 7 valence electrons. 2, 3, 4, 5, 6, 7. It was kind of blended together there. 1, 2, 3, 4, 5, 6, 7. Okay. So if copper's looking to lose those 2 electrons, might as well give it to something that's looking to gain electrons. So our copper is going to give up its 2 electrons over to chlorine and chlorine. Now, if you were coming at this problem fresh and I didn't give you the structure beforehand, this would just be like the other ionic problems we've dealt with kind of in the past. Copper would be looking to give up 2 electrons, and chlorine can only take 1. We can't just force it to take 2, and that would kind of mess up its octet. It would go to 8 valence electrons and then 9, and then that's too much. So we can't make one ion suffer just to make another ion happy. Okay? Instead, we just look for another chlorine atom. Okay? We can have as many ions of each of these 2 elements as it takes to make everything happy. Okay? So if I need more electrons to give away to something to satisfy it, okay, then maybe I can pick up a couple more cations. Okay? If I need something to soak up some more electrons, then maybe I can throw in a couple more anions. Okay? So these are expendable. Okay? We kind of have a pool of them to use and put together to make our compound happy. So in this case, we need 2 chlorines to make our copper happy, to give those 2 electrons away. We've got to have something that's going to take 2 electrons, which in this case is 2 separate chlorine atoms. So what we wind up with is copper with a +2 charge. We've shown its valence electrons have gone away. Chlorine, each is going to have a -1 charge. Oops. Because they started with 7 valence electrons, and they each gained 1. There we go. So this is our ionic compound, right? And the attraction between the positive and the negative is the ionic bonds that holds it together. To name this compound, again, we start with the cation, which is copper. And in order to tell how many electrons copper is going to give up in this case, 1 or 2 or 3 or 5 or whatever, we need to show that Roman numeral, which in this case is the Roman numeral for 2. So we read that out as copper 2. Right? Then we have chlorine. Then we chop the end off to make IDE. So this comes out as chloride. The formula then just counts up how many atoms there are of each thing. Okay? And again, be careful. We do not need the Roman numeral for this one. I'll see these 2 mistakes a lot. I'll see people write the Roman numeral into the formula. Like that. That's a no-go. Or to make it look like the subscript, they will put it down there. Okay. Either of those is not what we want. Again, we're writing how many atoms there are of each thing. We only needed 1 atom of copper to help satisfy 2 chlorine atoms. So our formula should be CuCl2. If I needed to turn this around and figure out what CuCl2 looks like and how many electrons copper is giving up, I just need to know that each chlorine can only take 1 electron. So therefore, if I've got 2 of them, my copper must be giving up 2 electrons. we can name this compound copper 2 chloride and give it the formula CuCl2. Okay, so hopefully you've seen that these aren't all that different from the other problems that we've done. The only curveball we've thrown in is this Roman numeral thing. And that just really is a helpful hint of how many valence electrons a transition metal in that kind of value of the periodic table is going to give up. Okay. So these last two are not going to be all that tricky compared to the other ones. But this time you got to draw this part yourself. Okay. So I guess in that sense, this is going to be a little tricky. And the other ones, at least you get to see kind of how many of each atom you're going to have, so that can kind of give you hints to make it all work out nicely. Okay, but in this case, it's all up to you. But I have faith in you. I think you can do it. Same goes for this last one. Okay, again, really the only curveball here is the Roman numeral. This just means that iron's going to end up losing 3 valence electrons. And should therefore have a charge of positive 3. Okay? And remember, we can have as many iron atoms and oxygen atoms as we need to make this thing happy, to get everything to an octet, to get iron to lose 3 electrons every time it shows up, and to get oxygen to gain 2 electrons every time it shows up. Okay? So, if your charges don't cancel and your stuff hasn't reached octets yet, keep going. Keep throwing stuff in until it works. Okay? You won't really see anything get bigger than what we kind of did in part 1 assignment, if you saw that. But it can still get a little bit nasty. But again, I have faith in you. I know you can do it.